Okay, welcome back. Happy Chilly Friday. Today is our very last day of new material for the semester. We're going to be talking about data fitting. Coming up on Monday, lots of stuff is happening. That's our review day for the final exam. Project 4 is due on Monday. That's for everybody. Quiz 4 is due on Monday if you want it to be. So if you turn it in, I will grade it, and whether it helps you or hurts you, it's going to count in your grade. But if you decide you don't want to turn it in, it won't help or hurt. It won't count for anything, okay? So optional, but if you turn it in, I'm grading it and counting it. Regardless of whether or not you're turning it in for a grade, you should work on all those problems on the quiz. It's just another good source of practice material for the final exam, which is coming up on Wednesday, right here in this room, 1 o'clock. Questions on the calendar? Okay, so just thinking about the final exam, you don't need to get to this page, but I just want to talk about the study guide for a moment. So here's what this one looks like, study guide for the final exam. And it's a list of things that I want you to be able to do if you are prepared for Wednesday's exam. And I think that a lot of people don't bother like really even looking at this list. They don't do anything with it. And I think if that describes you, you might be missing an opportunity. So let's take a look at number 12. You should be able to, given a transformation of a function, write an equation for the transformed function. So given a transformation, meaning you're looking at a picture or words, I want you to write an equation. And so in order to be prepared for Wednesday's test, I want you to get to the place where, you know, like you can read my descriptions up here. You can know what kinds of questions I might be asking you. And you also know the process that you'd follow to answer those questions. So given a transformation, so if I gave you a picture, like you imagine your parabola, like normal parabola is here and this parabola is up here. What kinds of things? How do you translate that to English and then an equation? So normal parabola is this one, and then yeah, so like maybe like a vertical, you know, like it's been pushed up by 2 and maybe it's been pushed to the right by 3 or whatever it is, but you got to imagine, okay, I'm going to be counting boxes something to figure out how far it's moved and in which directions. And then once you know, oh, it's to the right 3 and up 2, you then have to know how to write the equation. And so to write something move to the right 2, you change x to what? No, x becomes what if we're going to shift something to the right 2? X becomes x minus 2. Doesn't just become minus 2, it becomes x minus 2. All the x's become x minus 2. And if I want to shift something up 3, how does that appear in the equation? You put a plus 3 all the way at the end outside of the function, right? And then you can play the same game. That was shifts, but there's also stretches involved, and some of those can be kind of tricky, whether, you know, like does a half really mean half of everything, or does it mean double everything? And shrinks and reflections. Reflections had to do with negative signs floating around, but where the negative sign is had a big impact. And so like in my mind, I have a very clear sense of what kinds of questions you might get asked about that and the process for following them. But I've been doing this for a long time, and so you got to get to the place where in your mind you have that level of comfort, that you know what I might be asking and that you know how to handle it. And if you work through this entire list of 19 items, I'm hoping that you start to see some common threads maybe you didn't see during the semester. There's really not that many fundamental processes that we've covered this semester. And it's a matter of like saying, oh, I understand like if I want to plot a point, like if I know the x value, I just find the y value by plugging that point, the x, into the original equation. And that's something that we did in a variety of different contexts. Right? We had different reasons for needing to plug a point into the original equation. And so if you go through like looking at the whole semester like as a big unit, you might start to see some of these common threads and make some connections, okay? So like I said, I think that a lot of folks don't bother reading it. It's a lot of words. Maybe it doesn't feel helpful, but I think there is a way to get something very concrete out of this study guide. Okay, so let's go back and take a look at the demo for today. So we're on this page. It doesn't have a page number, but at the top it says class 39. Okay, so today is all about taking data points and then figuring out what kind of an equation might be an appropriate fit for those data points. And so there's a guide here that's supposed to help you. If you see dots that look like they're pretty much on a straight line, not going to be perfect, but if it looks pretty close, then maybe a linear thing. These next two look like parabolas. Maybe they are quadratics, x squared, some flavor of x squared. These guys here, maybe x cubed type equations, right? I see a max and a min. So if there's two extremes, then it's got to be degree 3 or higher. These next ones, quartic, that's a fancy word for degree what? That's degree 4, and you can see 1, 2, and 3 extreme points. So maybe degree 4. All right, and then we had some other ones more recently. Exponential. These two are both exponential. What's the word that we use for the first one? Exponential growth, and the other one exponential decay, right? And then we had logarithmic stuff, so that was something which grew very quickly in the beginning. It was actually a vertical asymptote, and then it grows but slowly. And then finally, the logistic one was the most complicated, where it grows slow and then fast and then slow as it levels off near the capacity of the environment. Okay, all right, so those are what we're looking for. And let's take a look at this example here. We'll start with this number 3. Data modeled with exponential and log functions are either always increasing or always decreasing. So looking at these pictures again, exponential growth, always what? Increasing. Exponential decay, always decreasing. Log function, always increasing. Actually, there is another kind of log function that looks like this. This should be something where the base is between 0 and 1. We don't talk about those graphs all that often. You might never have seen that graph before. But anyway, log functions could be decreasing, but whatever they are always doing that thing. And the really tricky thing here is that these two graphs, what do you think? They look very similar to each other. And so we need to like have some characteristics that we can tell them apart, because you're just going to have dots and you're going to have to try to figure out what kind of equation is most appropriate. So that's what we're after in this beginning of number 3 here. So let's take a look. The answers to these problems are either exponential or log. Part A, these functions increase or decrease rapidly at first, and then there's kind of a typo in there. They just increase or decrease slowly as time moves on. So which one does that describe? Is that an exponential thing or is that a log thing? It's a log thing. The log was really steep in the beginning and then grows slowly, 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 or maybe really steep downhill in the beginning and then shrinks, but slowly, slowly, slowly. So this is what we're looking for log functions. And then the other one, it says these functions grow slowly and then accelerate quickly without bound. That's an exponential what? Growth. It grows slowly in the beginning and then increases quickly without bound. Or if you think about the decay function, which was a steep in the beginning and then leveling off at the axis. Or they decay quickly at first and then slow down and get closer and closer to 0. So that was exponential, both flavors of exponential. Okay, so let's see if we can actually do something with some real data. So here is something about life expectancy. Due to advances in medicine and higher standards of living, life expectancy has been increasing in most developed countries since the beginning of the 20th century. So about 15 straight years, life expectancy has grown in most developed countries. I actually saw an article maybe a week or 2 ago that this has changed. Anybody see this? Yeah, where? In the US, for the first time in 30-something years. Life expectancy in 2015 was a little lower than it was the previous year. It had been increasing for about 30 straight years. It wasn't a change by much. I don't remember the numbers. Do you remember the numbers, Pete? It went from something like, I don't know, like 73.5 to like 73.2. It wasn't like a dramatic, off the cliff kind of thing, but it was the first decrease that we've had in a while. Okay, so here are life expectancies in years of Americans from 1900 to 2010, every 10 years. I'm going to give you the life expectancy. When I first saw this chart, I'd kind of like 47, right? Like imagine somebody passing at 47. Maybe you know somebody that passed in their 40s, right? Like that's just like incredibly young. But just 115 years ago, that was average, right? And so, there are plenty of people that live twice as long today as the average person lived 100 plus years ago. So we can see the numbers, clearly they're increasing, right? Every 10 years they're increasing, but I want to know more than that. I want to actually see how are they increasing? Is it kind of steadily like a linear thing, or is it increasing slow in the beginning and then faster, or maybe it increases fast and then slower? So you're going to do this with the graphing calculator in the activity. You'll have plenty of time to do this, so I'm doing this quick. The goal here is just to show you a little bit of the highlights. You don't need to follow along on your own calculators right now. Instructions are written out in the activities themselves. So all I did is type the data in, calling this guy 1 and this guy 2 and this guy 3. That's the first column. And then I just typed in the life expectancies in the second column. 47.3 and 50 are there. Okay, so that's just data entry. I did that ahead of time. And once I've done that, I want to see the data. And so the easiest way to see the data is to do second, and then right up here it says stat plot. I don't know if you can read that in the back. Second stat plot. And I want to turn that plot on. Actually, even easier than that. Scratch that. If you just go into y equals, you can see plot 1, 2, and 3. And if I just come up here and hit enter and move away, you can see that that one is now highlighted on. Okay. So if I hit graph, where are my points? Why aren't they there? Yeah, look, the y value starts at 47 and then goes up. So I got to get a lot bigger than the window here. So it is quite easy to just change the window to be something appropriate. If you're feeling really lazy or maybe efficient, it turns out the calculator will give you a nice window if you just know how to ask for it. And so if you go into zoom and then all the way down here, zoom stat for statistics, right? Zoom stat will find you a very nice window. Okay? So you can make it by hand if you're into like controlling your windows, but if you want to just trust the calculator to do its thing, zoom stat. Again, that's in the packet, the instructions for that. Okay, what do you think? We had all of these choices back here. All right, linear seems like a pretty fair thing, right? I mean, it's pretty close. Like a linear would not be a bad fit here. Anything else seem reasonable? Which one of these logs? First one. I mean, like maybe we're looking at this part, like not so much the steep in the beginning, but logs do grow forever, but slowly. And so maybe life expectancy is going to grow forever, but slower and slower and slower. This is supposed to be something that's slowing down as opposed to linear, where it's just like every 10 years, people grow another, like life expectancy increases by the same 2 years every single time. So I think that there's actually something to be said for something where the life expectancy grows, hopefully forever, but like by less and less and less, right? Unless there's some dramatic like medical shift, something that just like is a game changer, probably we're looking at like something that's more log than linear. Okay, so here's how we get the calculator to find the best fit log equation here. And again, the instructions are in your packet. We're going into stat and then over here to calc. One of these things we have played with before, this lin reg stands for linear regression, and that will find you the best fit line. We've done that before, but you can see now, if we just look a little bit farther, we've got quad reg. What do you think that is? That's quadratic, right? So we had all of our choices here. So quad reg will give you the best fit parabola. And the next one, cubic regression. Okay, that's something like that. What's this? Quartic regression. Okay, that's fair. And then we'll keep going. All right, then we got linreg again. I actually honestly don't know why they have two of these. There is a subtle difference. Do you see it? Yeah, here the X is touching the A and here it's touching the B. I don't know why. I think like some kinds of like math, like statistics uses like one, but then like the rest of the world uses the other. I don't get it. What about this? Let's skip number 9 for a second. How about 0? Exponentials. That would give us one of these guys. We haven't talked about this one, but what is that? Power reg. We haven't talked about power functions, but if you're feeling like very like forceful today, you can experiment with it. That was a little joke there. See, thank you. Okay, next one, logistic. Okay, there's no guessing there. That's one of our functions, something like that. And down here, it's a sine. Yeah, it's a sine regression. We haven't talked about the sine function, but if you imagine like a sine wave just kind of going up and down and up and down, you can try to fit your data that way. All right, so the one that we skipped is actually the one that we want. There was one in here that we didn't see. Which one didn't we see? Which one? Well, yeah, that's what we want. We haven't seen it. There's no logarithmic one in here. There's no log one that we did. There's a logistic, but that's different. But what do you think ln stands for? log. That's the natural log. So ln is not line, it's the natural log. Just like you have an ln button right over here on your calculator. So that's the one that we want. And we hit enter, and we just have to tell it where the data is. Again, the instructions are in your packet. And then I want to tell it, I want to graph the log function. I don't want it to just tell me the equation. I want it to see the picture along with the data so I can judge if it's a good fit. And so I needed to say y1 right here. That's going to be my way of telling the calculator to put the equation it's about to come up with in the y equals. I want to put it right there. And so I think you've done this before, but y1 is inside of vars, variables. It's inside of y vars right there. Function is good, and there's your list. And so lots of buttons. Again, the instructions are there for you, and I can help you during class. And there you go. The form that it's giving you is a plus b ln of x, where a is around 42.5 and b is a little under 14. So 42.5 plus about 14 times ln of x. And all of that stuff is now typed quite nicely in there, okay? And so if I hit graph, it's going to show me the data, and then it's going to show me the curve. So first of all, does that graph look like our logarithmic picture over here? It sure does. Okay. All right, what do you think? Is that a good fit for the data? Yeah, it looks pretty good to me. I mean, it's, it's off by a little bit down here. It's not perfect, but it's hugging these points pretty darn well. Okay, so we've got our equation, we've got our picture, we're happy with the fit. Again, all right, so there's the equation that we just came up with here. And let's move on to the next page. There's the graph. And now we're going to use the equation in order to do some calculations. So it says use the model to predict life expectancy for the year 2030. 2030. All right, so don't forget, what we did was call this guy here 1, and this 2, and this 3, and this 4. So if I'm looking for 2030, what x value is it? It's 14, right? So it's 14. It's kind of a strange thing. It's not so strange to do every 10 years and just not write the zeros, right? Like instead of doing 10, 20, 30, we just do 1, 2, 3. But what is a little bit strange about calling 1900 1? Is there like another natural choice you could have called 1900? Maybe 0? Like, don't we almost always just say whatever the first data point is, let's just call it 0? So the issue here is that you remember the graph of our log function looks like this. So y equals ln of x. What is ln of 0? Look at the graph. What do you see happening at x equals 0? It's not possible. We've got this vertical asymptote at the y-axis, right? ln of 0 does not exist. Calculator will say domain error or something like that. So if I try to put a 0 there for the x, ln all of a sudden is not possible. It's just, you can't make a graph with ln hit the y-axis. So that's why we have to do this kind of funky, just shift it off by 1. Okay, so apparently 14 is the number we're looking for. So let's plug 14 in. Can somebody read to me some of the equation from the previous page? Is it 35? Y equals what? Okay. Okay. So ln of x, and then the only change we're doing here is ln of 14. That's all. And so you might want to know, okay, well, how many digits do I need to write down? All right, so the instructions should be clear. It should say nearest thousandth or something like that. But the nice thing is that we don't have to worry about losing accuracy if we just know how to use our calculator. And so really what I'm interested in is plugging 14 in for the x, right? And if I go into vars and then to the right, and then say, hey, y1 of what number? 14. This is just our way of saying plug 14 in for the x, right? This is the most accurate answer the calculator can get. A whole lot less typing than like writing all this and then typing all this. That's the best way to do that. Okay, so about 79.1. Sounds good to me. Oops. Okay, and then there's a sentence here. If life expectancy continues to increase at this pace, I'm actually not a fan of this phrase right here. Continues to, I'm going to change that, something like that. Continues to grow logarithmically. Logarithmically. How about something like that? We're assuming it's a log. If it continues to behave like a log, then our prediction will be pretty accurate. Average life expectancy of an American will be how much by the year 2030? 79.1. That's it. Okay. All right, and then before you jump into the activity, just some words to live by. So typically you'll make a scatter plot. You're going to try maybe a few different types of functions to see which one appears to fit the data better. The more data you have, the better, obviously. If you have only a few data points, then any prediction we make is going to be with a big old grain of salt, right? Okay, you're going to compare your scatter plot with the features of all the functions that we just talked about. There is this business with R. We've talked about the R. Have we talked about the R? Did we not talk about R? R. That was one R, yeah, the remainder. Let's see here. Second catalog. Did I talk about turning diagnostic on? Does that sound familiar at all? Am I just making stuff up? One more time. So by turning diagnostic on, I've told the calculator I want this thing called R. R is just a measure of how well the data fit the model. If the data perfectly fit the model and it's increasing, R is equal to, anybody remember the magic number? It's 1. Yeah, like if the perfect linear fit, everything is ideal, R equals 1. If it's perfect linear fit, but like downhill, what was R? It was -1. And every other R that isn't perfect is going to be something between those two perfect extremes, R equals 1 and R equals -1, which means what value of R would be the absolute worst, like there's absolutely no relationship between the data and the model. 0 is in the middle. So really we're just comparing like how far from 0, which would be like the worst, trying to get close to maybe 1 or -1. So in this case, R is 0.978-ish, which is fairly close to 1. So that's a pretty good model. And you can try other models and see what kinds of R's you get there too. But it's not just about the R. Let's see here. It says find the equation. A simple model that fits the data reasonably well is preferable to a complex model that fits it slightly better. And we also want to look at this next phrase here. It says you want to pick something that has a realistic end behavior. And so Aaron had talked about what kind of model did you think maybe when you first saw the data, Aaron? Yeah, maybe linear, right? I mean, it looks fairly straight, so we can ask for a linear model too. That's no problem. So stat, and then over here, and then number 4. Let me say L1 and L2. And this time I'm going to ask it to graph the thing inside of Y2. And right there, 0.97, that's really close to the same. It's almost exactly the same R as before, and we can graph. The first one is the log one. And then the linear one is going to go through. And so like it does, well, let's see. I don't know. What do you think? Which one do you like better? Maybe the log one. I mean, the linear one, like it, kind of like cuts through, but it like sort of is like under significant, like it's consistently under, and then it's consistently over, and then it's consistently under, or maybe I said that backwards. But the real issue here, I'm going to go out here. So this 13.1, that goes to 2030 or 2020, I think. I'm going to pump this up to like 100, and I'm going to go higher on this guy too. Let's go up to like 300 or something. So that's just my way. All right, so that shaded stuff is the data. And this was the log graph, and this was the linear graph. So I'm hoping that you can see why maybe the log one is potentially more reasonable. What am I illustrating here? Yeah, I mean, like, look at, like this is like 100, this is, let's see, 100 times 10. So it's about 1,000 years into the future. Like, according to this one, yeah, the life expectancy continues to grow, but it's fairly slow, the growth, right? Whereas here, This is one of those game-changing things where, like, you know, like we would be living like hundreds and hundreds and hundreds of years if this is accurate. And so even though like in the short term, they both looked pretty darn good and the R value was pretty close, you kind of want to think about end behavior as well and make sure you're picking a model that sort of jives with what you think reality might be. Any prediction is difficult, but you want to sort of be aware of like, well, what, you know, like what am I really saying 100 years from now, 500 years, 1,000 years from now if I pick one over the other? Okay. All right. I think that that is good. Oh, and the last one here. If you are using your equation to find values between known values, like something between, you know, 1900 and 2010, I think was our table, you are probably going to be more accurate than if you try to use your equation to predict things outside of known values. Try to predict before 1900 or after 2010, something might change, who knows, right? So it's always generally more accurate to interpolate than to extrapolate. Okay, so the class activities are there. They're pretty lengthy today, so let's see how far we can get. Again, any calculator questions, just raise a flag and I will help. Do not waste a lot of time on calculator stuff. And if you don't have a calculator, come and trade me your phone.